When in a question you have to expand brackets, you may find that the power of said bracket is rather high, and it's probably not going to be worth your time and effort fully expanding that manually. Say, for instance, we have 1 plus 3x squared. Well, that's just to the power of 2. That's fine. That just means that it's the bracket times itself. So you have 1 plus 3x times 1 plus 3x. Now we'll expand this as double brackets. So first times first is going to give us a value of 1, because 1 times 1. Outer, 1 times 3x will be 3x. Inner, 3x times 1 is 3x again. Collect the like terms. 3x add 3x is 6x. And then the last terms, 3x times 3x is going to give us 9x squared. Fairly straightforward. But what if instead we hadn't had a power of 2, we'd had a power of 9? Now we wouldn't want to have to write out 9 of these brackets and times them all again, one by one. Take this quadratic, times it by the bracket. Take the cubic that makes and times it by the bracket. It would take too long, and there's a risk you'll make a mistake along the way. So what we can do instead is employ this topic here, binomial expansion. With binomial expansion, this is a formula we can use to work out what the fully expanded terms within a large powered bracket would be, so long as x is within a suitable size range. I'll clarify what I mean by that at the end of this explanation. To start off with though, just to present the formula, if you had a plus bx, then in brackets to the power of n. Each term in this expansion would be made up of 3 parts. So you have NCR. The NCR is a button on your calculator. You may have to hit Shift in order to access it. It's basically saying if you had n an amount of terms, how many different combinations could you have if you wanted to take R from that n? And again, I'll just show what I mean by numbers for that in a second. But then timesing to that, you have your second component, which will be your a term to the power of r, there's n minus r, so this number minus this number. And then lastly, times by bx, which is as an entire phrase, to the power of r. So these two powers here should always add up to make the n value here, which was the power of the original bracket. For your terms then, you'll start with NC0. Then from here we'll have a to the power of n and bx to the power of 0. Obviously this is going to make the bx term disappear because anything to the power of 0 is 1 and times by 1 makes no difference. And that makes sense because if we look at the original expansion for the quadratic, the first term doesn't have an x in it, it's x to the power of 0. As we then go forward, it's probably going to say like in ascending powers of x, so as x power starts getting bigger and bigger, you now have NC1, where you then have a and n minus 1, and bx to the power of 1. Following that, you'll then go up to NC2, a to the n minus 2, and bx to the power of 2. And this will keep on going until you get to NCn, a to the power of 0, and bx to the power of n. So what you should find is that each time your a power is going down by 1, your bx power is going up by 1, until you end up just completely flipping the scales to go from one extreme to the other in the opposite directions. Also within the question, it's very unlikely that you're going to have to expand all of these terms. I'd say maybe at most they want you to do 5 terms, as in if it was to the power of 5. But usually they'll say something like, what's the first 3 terms of this expansion? What's the first 4 terms? Now this does mean that your expansion is then only an approximation rather than truly accurate. However, and this gets back to the idea that x has to be within a certain range. I'm going to explain that. But because x is in a certain range, it has to be smaller than something. What that means is as you keep raising the powers, your x value actually gets smaller and smaller until the point where the higher brackets are actually negligible in terms of x. They're basically not adding anything anymore, so we can ignore them. It still works as an approximation. So just to finish off what was started above, if we have this 1 plus 3x to the power of 9, and let's say we want the first 4 terms. For the first term, we're going to have NC0, and our A term is 1, so that N should be a 9, so it's the power of 9, and then we're going to have 3x to the power of 0. I'll simplify that in a second. We'll just write the expressions first of all. Then for the second term, 9c1, and then 1 to the power of 8, and 3x to the power of 1. You'll notice here that the r values are 1 less than the number of terms in the sequence. So the first term r is 1, first term r is 0, second term r is 1, so forth. Then added to that, you have 9c2 for the third term, and 1 to the power of 7, and 3x squared. And then because we're after 4 terms, 9c3, 1 to the power of 6, and 3x to the power of 3. And this will keep on going. This, therefore, we can say is approximately, you just plug this into your calculator. In terms of the x, if you just take the x to that power separately, just focus on the coefficient. So 9 choose 0 times 1 to the power of 9 times 3 to the power of 0, that's just 1. Again, 3 to the, so x to the 0 makes no difference, so it's just first term is 1. Adding to this, 9 choose 1 times 1 to the power of 8 times 3 to the power of 1 gives us 27, and x to the power of 1 is just x. And here, 9 choose 2 times 1 to the 7 times 3 squared, that gives us 324 x squared. And finally, 9 choose 3 times 1 to the power of 6 times 3 to the power of 3 is 2,268, with x being then cubed. And again, that would keep on going. You can see here already how quickly the coefficients start to get bigger, potentially. If you think about it, if you were to times this together 9 times, you've got 3 times 3 times 3 times 3, you're going to get to high values very quickly. And also again, if you were to work out an actual approximate value, you can now then use these few terms here, plug in an x value that makes sense, and then just put that in your calculator and get an answer. Now we come to subbing in those x values though, I'll get to that point I was alluding to before, about the x has to be within a certain range of values for this to work. If our a is 1, and in all honesty the majority of these questions it will be, you need the modulus of your bx, in this case a 3x. This has to be less than 1. If you're not familiar with the modulus symbol, I'd advise that you watch the video on that. But in general, we're saying that regardless of the sign, whether it's a positive 3x or a negative 3x, it has to end up being less than 1. So 3x has to be between -1 and 1. Therefore, the modulus of your x has to be less than a third. So our x value this will work for if it's greater than minus a third, but less than positive a third. And that's how then you get this idea that for the greater x powers, it gets smaller and smaller, and thus those high terms become negligible. Again, though, the main thing you just have to worry about is this formula. So actually, let's just move on to see how we can employ that in another example, where perhaps we don't have quite as much information as we did down here. Given that the expansion of 1 plus px to the power of 12, that in the expansion, the coefficient of x is q, and the coefficient of x squared is 11q, work out p and q. So what we're going to have to do is expand this as best that we can, and then look at what coefficient that gives us for the single x term, for the x squared terms, and say those are the same as your q and your q and your 11q. And then because p is going to be the same as p and q is going to be the same as q, we can then just treat these as simultaneous equations. To start expanding then, for the first term, we're going to have 12 choose 0, 1 to the power of 12, and then px to the power of 0. As I did it down here, I'll simplify that in a second. Just to write it all out first though, 12 choose 1, gets us then 1 to the power of 11 plus px to the power of 1. And then for the third term, 12 choose 2, 1 to the power of 10, and px to the power of 2. We only need to go up to x squared, so I'm not going to bother going any further. Putting this in the calculator, 12 choose 1 times 1 to the power 12, and then p to the 0 just disappears. You end up with the first term just being 1. And here, 12 choose 1 times 1 to the power of 11 times p to the power of 1. That's going to give us 12p, and then x to the power of 1 is x. And thirdly here, 12 choose 2 times 1 to the power of 10 times p squared is going to give us 66p squared, and then with the x squared as well. Comparing coefficients, we can therefore say that, okay, this coefficient of the x term is 12p, so therefore 12p must be the same as q, and then also the 66p squared must be the same as the 11q, because again, there's both for the same expansion, they're expressions for the same amounts of those x terms. Just simplifying this right-hand one though, so we can divide through by 11, you end up with 6p squared equals q. And now, because both of these expressions equal q, you can just set them equal to each other. So 12p equals 6p squared. Divide through by the 6, you end up with 2p equals p squared. And divide by the p, you end up with 2 equals p. Therefore then, if we just plug that into here, if q is 12 times p, then q will equal 12 times the 2, which makes your q value 24. If we can see what we've done there, and we're happy again with just how you can adopt this formula in a slightly different way, let's have a go of doing a question on your own. So find the first 4 terms in ascending powers of x, so you're just going from no x up to x, x squared, so forth, of 1 plus x over 4 to the power of 8, and so find an approximation for the value of 1.025 to the power of 8. So we've got things that are slightly different this time. Think about what your actual bx term is. Think about how, when you've done that, that might relate to this. Pause the video, have a go for yourself, and then press play again when you're ready to compare. So we need to find the first 4 terms to begin with, so let's do the expansion. To begin with, you've got n is 8, and you'll do c0. That leaves you having 1 to the power of 8. And then if we want for the bx, if we want to clarify b as a separate part to x, b could be a quarter. So a quarter x, and in this case it doesn't make a difference because it's the power of 0. But in the next instances, 8 choose 1, and then that's 1 to the power of 7, and a quarter x to the power of 1. Plus 8 choose 2 times 1 to the power of 6, and then a quarter x to the power of 2. And then just to round off with, because we're doing the first 4 terms, 8 choose 3, 1 to the power of 5, and a quarter x to the power of 3. Plugging these now into a calculator, for this first one, you should just once again get a value of 1. And here, you should get 2x. Here, you should get 7 over 4 x squared. And here, you should get 7 over 8 x cubed. Okay, so these are the first 4 terms of your expansion. Now that we have these, we can work out what we can do to get an approximation for that value there. If we notice again, it's obviously both to the power of 8, and they're both something more than 1. So if we've already accounted for the 1, that leaves this plus x over 4 making up for this 0.025. So x over 4 equals 0.025. Therefore, if we times up by the 4 to leave the x on its own, x is going to be 0.1. Now, if we know that if x is 0.1, that will be the same as if it was 1.025, then in each case the power of 8, we can therefore say an approximation for that expansion is going to be just this expression here, except we've replaced all the x's as 0.1, So 1 plus 2 times 0.1 and so forth and so forth. That gets to you that 1.025 to the power of 8 is approximately 1.22 if we were to do it to 2 decimal places. It's only an approximation because, of course, we haven't done every single term in the expansion. We haven't gone up to x to the power of 8. But if you were to put in 1.025 to the power of 8 into a calculator as it is, you would find that decimal is very close. Good with that? Let's just wrap up by looking at an actual question. So here we are told that find the first three terms in ascending powers of x of the binomial expansion of 2 minus x over 16 to the power of 9, giving each term in its simplest form. Well, in this case, if we're just going to do the first 3 terms, we'll start off with our 9, choose 0, and this time, different to what we had before, the a is going to be a 2, so 2 to the power of 9, and then here we could say that this is going to be minus a 16th x if we wanted, and that's of course going to be to the power of 0. For the second term, you're going to have 9 choose 1, and then 2 to the power of 8, minus 1 over 16 x to the power of 1, and after the first 3 terms, so we want more, 9 choose 2, 2 to the power of 7, and then minus 1 over 16x to the power of 2. This, of course, we are going to have to expand or simplify. So 9 choose 0 times 2 to the power of 9, but that power of 0 makes no difference. You get a first term of just 512. And here, 9 choose 1 times 2 to the power of 8 times minus 1 over 16 to the power of 1 gives you minus 144x. And then here, 9 choose 2 times 2 to the power of 7 times minus 1 over 16 squared. Be sure to put the minus 16 in brackets before you square it, otherwise it will do the minus afterwards rather than before. Minus squared gives you a positive again, so you end up with positive 18x squared, and so it would continue. And again, you notice here, because this b value is a fraction, the greater the power, the smaller it is, and that's why the coefficients are actually getting smaller this time. Now that we have this, we're saying that the function of x equals a plus bx times this bracket we had before to the power of 9, where a and b are constants. Given that the first 2 terms in the ascending powers of x in the series expansion of fx are 128 and 36x, find the value of a and find the value of b. So we know the first couple of terms of this expansion are this, but now this quadratic is being times by this other bracket here. If we just dealt with that over here, so I'll just rewrite it out again, so a plus bx, and that's times the 512 minus 144x plus 18x squared. Timesing this out, so a times the 512 gives us 512a, so basically a times each of these terms, so you get minus 144ax and plus 18ax squared. Then do the same with the other terms, that now becomes plus 512bx minus 144bx squared, and then plus 18bx cubed. Now what we're looking for here is the first 2 terms. So this will be our first term because it still doesn't have any x. And then for the second term, it's going to be the combination of this and this, because they are both terms which just have a singular x. They would be grouped together as like terms. So in terms of the first term, because we already have that just as a single thing, we're saying that this 512a, that's the same as the 128. Therefore, we can say that a will be 128 divided by 512, which is going to get us a simplified value of a quarter. Now that we know that a is a quarter, we can turn to the next bit. So minus 144 times a quarter x plus 512b, x, we don't know what b is. This is going to be the same as 36x. Because these are all in terms of x, we can actually just kind of ignore them. Just look at the coefficients. The minus 144 divided by 4, that's just going to be minus 36 plus 512b equals 36. Add the 36 over, 512b equals 72, and so b is going to equal 72 over 512, which will simplify, if you put that in your calculator, to 9/60.